all the possible states of one qubit. Okay, so this is one qubit.
Yeah.
Now all the possible states, all the points on this sphere would represent the all the possible
Raised to power 2. We'll
2 raised to
start.
power n. N qubits represent 2 to the power n number of states.
And number of states. Okay. At the same time, we will have two states.
Okay, yeah, yes. So this is one single qubit. So it has
Yeah.
two different states. So if you
Yes.
see 0 and 1,
0 and 1, right?
so two different states. And if you come here, if any point on this would be a linear combination of these two states. So if
Okay.
I look at this equator, it means I have 50-50 probability of getting 0 or 1.
1, right?
So any point on that would be basically a quantum state. Since this whole thing represents the total possible quantum states of one of Bloch sphere is only for one particular qubit.
Okay.
Okay. So since this is a 3D representation of one particular qubit, for Bloch sphere for 2 qubit, you are in 15 dimensions of expressibility. I am under parameterized and I cannot represent the target states. I am going to do my basically the model is going to be underfitting. If I have too high, if I have too many number of parameters, may suffer from my gate operations on 2 qubits. I am doing entanglement between those 2 qubits. And
Okay.
this
Okay.
thing is much more fundamental for quantum advantage in machine learning and for optimization.
Okay.
Okay, so how do you measure entangling capability? You have something known as entanglement entropy and Mayer-Wallach Q measure. Now, entanglement entropy is, let's say I have an n qubit system. Okay, I would randomly choose a k. Okay, I would separate them out. Okay, 0 to k and k plus 1 to n. Two different halves. Now I would do von Neumann entropy on both of them. Okay, to basically on the k part via partial trace method. Okay, it is a partial trace method. It's a mathematical method which would help you to do and find out the von Neumann entropy, and with that von Neumann entropy you would be able to find out if these two halves are basically entangled or not, or connected or not. But this disadvantage of this is it does not basically it gets hard as the number of qubit grows. If my n qubit is in millions and I need to find out the best entanglement half, I would have to basically do from 0 to k, 0 to n. And your it also depends on where you are cutting. Okay, if I'm cutting in the first, let's say 0, and all the rest thing is cut, so that may not be entangled, but some other part may be entangled. So this particular entangled entropy measure tells you which qubit is entangled to which, or which half is entangled to which. But there is another way of measuring entanglement. It is Mayer-Wallach entropy. It is also, again, you would have to do mathematical combinations on the density matrix. Okay, partial traces and everything. Then you get the overall entanglement of your basically quantum states. Mayer-Wallach basically is between 0 and 1, 1 being maximally entangled or a belt state, and 0 being no entanglement. But Mayer-Wallach score tells you how overall connectivity is there, but it does not say which qubits are talking to which. So it won't say qubit 0 is connected to qubit 1. It would only say that we have this much entanglement in our circuit, but we do not know which qubit is connected to which. Now the thing is, you have to design your ansatz, you have to design your quantum circuit. You have hardware efficient way. Your quantum computers are much more have some. These are the edges. Sorry, these are the vertices, and this
Vertices,
is
and these are the edges, right?
wherever edges are there. There,
From one node to the last node. Matlab, if we are taking this diagram as a single one, So from the starting, there is no starting one. Na? We have to go by this only.
No. When designing it, just go into Qiskit. There is Circ, Penny Lane, CUDA Q, to basically all these different fragmented simulation frameworks, or even
Yeah. In our CDAC, you are from CDAC
yes,
Pune, right?
CDAC Bangalore.
Okay, CDAC Bangalore.
Yeah,
Okay.
that is what I'm saying.
Email ID, and will certainly note give a mail to the sir, and will visit in the month of January after your exams.
Yeah. Please basically do it so that we also give you a correct deadline or correct date.
Yes,
At
actually, the students they will have their exams in the month of November, December, so they may get free by January. So, will January we will certainly, you know, I will write down a mail to you and will get the permission. Who is
sure,
the
sure.
coordinator of this event? Kindly note down the email of the sir. Okay.
Yes, ma'am.
Universe at cdac.in. Okay.
Placement and
Upcoming
interview
world.
cell.
Upcoming
Yes,
world.
yes, yes. Then they may require all this. So this is
Yes.
actually a good platform, sir. Very nice. I will certainly uh, I will share my email ID as well as the mobile number with you on
Sure,
your
sure,
mail
sure.
ID. Then we
If
will.
you want, you can note down my email ID. My email ID is this. Okay. Linear algebra is mostly used in quantum computing. But also, if you are just a CSE student, you also need to know the programming languages as well. So if you want to do quantum computing aspects. Now if you have any further specializations, like I have specialization in machine learning, or if you are much more specialized in cryptography and you know how basic maths work in post quantum cryptography. Okay, there are two types of crypto things there. Post quantum cryptography is basically dealing with cryptographic algorithms which are quantum secure. That means it can run on classical computers, and but quantum computers would take years to crack it, unlike RSA, which can be cracked much more faster. So, as a fresher in BTech graduate, whatever field you have done, it does not matter electrical or whatever is there. What you can do is, if you want, if your basically college is in NIRF ranking 100, okay, you can basically ask CDAC. We would visit. We would do on-campus recruitment.
Sir, thank
Okay.
you. Sir, thank you so much for a such insightful and engaging session. We
Thank
really
you.
appreciate you taking the time, share your knowledge and the experience with us. As a small gesture of our gratitude on the behalf of SVI IEEE chapter, I have honored to present this virtual token of appreciation
Thank
to
you. Thank you.
you for being the part of the IEEE Pass series. Just I share your screen to this part.
No issues. No issues. No issues. Your heartfelt thanks is much more required.
Thank you so much.
Uh, I'm writing my. I have written my.
This is sir. This token is your small way of saying thank you to your valuable time and knowledge that provide us about the quantum computing. And thank you so much, sir, for a wonderful day and a session that you provide us and our students who can participate from different college and different branches. They learn a lot about the quantum computers from you. Thank you
Thank you.
once again, sir.
Thank you. I have written my mail ID and my number. If you still have any doubts or if you still want to know more about it, you can contact me here. And for example,
Further, any lessons?
Thank you, sir.
wait, somebody's asking my LinkedIn as well. Wait, let me show you my LinkedIn as well. That is also going.
Okay, sir.
If you still
Shall we
have
end?
any, if you still have any doubts, you can ask, or shall we end this session?
Any participant have any queries or doubt? No, sir. I think all covered.
Okay, okay, okay.
Thank you, sir. Thank you so much, sir. Once again.
Thank you,
Thank
thank you, thank you, thank you,
Thank you, sir.
Thank you so much, sir, for the wonderful session.
thank you, thank you.